Hello. Today we're going to talk about using the alpha carbon of a carbonyl as a nucleophile. This is going to be a very powerful reaction moving forward in our organic chemistry journey. So the first thing to look at is here we have a carbonyl. In this case, this is an aldehyde. Now, the proton adjacent to the carbonyl, or bound to the carbonyl carbon of the aldehyde, is actually not very acidic. This is a common mistake that people make because they see it close to an oxygen atom, they think it's going to be very acidic, but it's not very acidic. And it's not very acidic because once you've deprotonated this carbon, once you deprotonate this, you cannot use any resonance structures to stabilize the anion. Now, the proton adjacent to the carbonyl carbon on the alpha carbon is actually relatively acidic. And it's acidic, again, because once you've deprotonated it, this negative charge on the carbon can be stabilized through a resonance structure, putting that negative charge on the oxygen atom. All right, so again, this carbon is now a nucleophile, and it's stabilized by the fact that it's adjacent to an oxygen atom. So if we take a carbonyl and we treat this with a strong base, like LDA, it's a very commonly used base in organic chemistry, we can irreversibly deprotonate this carbonyl carbon. Oftentimes we draw the arrow pushing mechanism where we remove the proton, the base removes the proton, that carbon-hydrogen bond, the electrons go into forming a double bond between these two carbon atoms, and the electrons on the carbon-oxygen carbonyl wind up on the oxygen. This is now referred to as an enolate. Now the enolate, again, has the reactivity of the carbon alpha to the carbonyl being a nucleophile, and this resonance structure helps us to understand this reactivity. If you treat these with an electrophile, and we'll see an example in the next slide, they will form a carbon to electrophile bond, and again, this is a really powerful carbon-carbon bond forming reaction. Another thing to note is that the oxygen atoms of these enolates are also nucleophilic, and in some conditions you will form oxygen to electrophile bonds as well, and it depends on what electrophile you're using and what carbonyl you're using. Today we'll be talking about the alpha carbon as the nucleophile. All right, let's look at an example, a really common reaction. This is referred to as an aldol reaction, and you might be saying to yourself, well, how am I starting with this 2-carbon aldehyde, acetaldehyde, and receiving a 4-carbon product? So what's happening is the aldehyde is actually reacting twice. One equivalent of the aldehyde is being deprotonated at this alpha carbon to make it a nucleophile. The other aldehyde is acting as the electrophile. Remember, carbonyls have electrophilic character to them. There's a delta positive on the carbon and a delta negative on the oxygen atom. If you don't remember why that's the case, you can look back to carbonyl reactivity videos. So we simply react our nucleophile with our electrophile to form a key carbon-carbon bond here, and you also now receive a deprotonated alcohol. That alcohol can be protonated by the water, which is all around it, and this now gives you a beta alcohol, an alcohol that is alpha beta to the carbonyl. Sometimes I like to draw in the carbon-hydrogen bond to remind myself that's what's there. Many times these reactions don't stop at the aldol reaction, but instead they do what's called an aldol condensation, and that is when the base comes back in and the molecule undergoes an elimination, so it's removing water, you're condensing water away from the material to give you now what's called an alpha-beta unsaturated carbonyl. And these alpha-beta unsaturated carbonyls are more stable than the products because having conjugation in a product is a stabilizing feature. So let's look at how this occurs. You take your alcohol and you now deprotonate it with the base. You deprotonate it, and again, that carbon adjacent to the carbonyl is relatively acidic. And so now you have a negative charge on this carbon. You could draw it as the enolate if you want to. You don't have to. This now is able to kick off hydroxide as a leaving group and give you this alpha-beta unsaturated product. And it regenerates the base. So this can be done catalytically in the presence of base. Something to note is that I had previously told you that hydroxide, or the OH minus is not a great leaving group, and it isn't, but this is different than a normal elimination reaction that we've seen before in the like an E2 elimination reaction. This elimination reaction is referred to as an E1CB. The CB stands for conjugate base. So it's analogous to the E1 reaction we saw before, where before we saw a carbocation forming under acidic conditions, where you've paid an energetic cost and you've made a reactive intermediate that then goes on to form an elimination product. This is analogous, where once you've deprotonated your starting material, you form this high energy intermediate that is able to kick off the hydroxide as a leaving group. Let's look at another reaction. There are many other variations of the alpha carbon acting as a carbonyl, acting as a nucleophile, but we're just going to look over one more today. And that is where I shouldn't skip so quickly, is you treat an ester with a base, and now the ester acts as both the nucleophile and the electrophile. So, if you treat this methyl ester with a relatively strong base, potassium t-butoxide, you will deprotonate it on the alpha carbon, and that generates a nucleophile. Another equivalent of the ester is acting as an electrophile, and again, the delta positive, delta negative, it's going to react like an acyl transfer reaction. We've seen these before, and you can refresh your memory on that video from before. This gives us a tetrahedral intermediate, which can then collapse down to regenerate a carbonyl. This gives you now a alpha beta keto ester, a beta keto ester product. And you might be saying to yourself, well, the ketone is more reactive than an ester. Isn't that going to create an issue? Isn't that going to keep reacting? Well, this has a trick up its sleeve. That trick happens to be that this proton here between the beta keto ester, this alpha carbon, is very acidic. And it's very acidic because once you've deprotonated it with the base that you just generated up here with this methoxide, you now have a carbon that is stabilized by resonance structures on both sides. So resonance structures can be additive in the context of acids and bases. So this is a very stable conjugate base, and so much so that you cannot use catalytic base. You have to use a stoichiometric, a full equivalent of base, because it gets trapped in this thermodynamic trap. This reaction happens to be called a Claisen condensation. There's many variants of Claisen condensations. There are intramolecular, where you can form cyclic products. That's called a Dieckmann cyclization. And there are, again, this is one style of using the alpha carbon as a nucleophile, but it just opens up the door to seeing that there's lots of other types of reactivity that's out there. Well, I look forward to any questions you have, and I look forward to potentially going down this path a little more in depth in the future if that's what you want to see. Thank you for your time.